On September 2, 1859, the sky caught fire. Observers as far south as Cuba, Jamaica, and Hawaii looked up to see blood-red aurora stretching across the night. This 19th century engraving captures the phenomenon, showing a ship at sea entirely dwarfed beneath a massive, glowing aurora borealis arch. Down on the ground, the effects were immediate and chaotic. Inside telegraph stations from Boston to Portland, equipment sparked violently. Paper feed strips caught fire. Operators were receiving electric shocks directly through their telegraph keys. Realizing their chemical batteries were fighting a massive influx of electricity from the sky, the operators tried a radical solution. They disconnected their batteries entirely and found they could keep sending messages powered solely by the ambient current rushing through the wires. We now know this as the Carrington event, the most intense geomagnetic storm in recorded history. This is astronomer Richard Carrington's actual sketch of the exact sunspot clusters that triggered the surge. What this storm revealed was that humanity had accidentally constructed a planetary-scale antenna. By stringing copper and iron across continents, they had built a communication system that was inherently exposed to the electrical whims of the atmosphere. To see the scale of that vulnerability, look at the physical footprint of the mid-19th century telegraph network. As we see on this map of North America and Europe, the system relied on tens of thousands of miles of bare iron wire strung endlessly across wooden poles. This vast web faced two constant electrical threats. The first was the slow, steady buildup of atmospheric electrostatic charge. The second was much more violent, direct lightning strikes injecting sudden surges of up to 3 million volts that barreled down the wires. In the 1850s, the electrical engineering toolkit was almost entirely empty. There were no modern solid-state surge suppressors, no metal oxide varistors, and no automatic circuit breakers to halt a surge. Without modern electronics, Victorian engineers had to rely strictly on the brute physical laws of nature to isolate the current and keep their operators from being electrocuted at their desks. The first line of defense started on the poles, facing the daily challenge of wet weather. Engineers needed a way to prevent low-voltage signaling current from leaking out of the wire and bleeding down the wooden poles into the earth during rain or fog. Early attempts used porous earthenware or iron-shielded glass insulators, but these often failed in the field. Capillary action would draw water into the core, creating a liquid bridge for the current to escape to the ground. The breakthrough came through mechanical geometry. This classic glass pony insulator has a threaded base and a wide outer shed designed to shed water. In cross-section, the mechanics are clear. Though heavy rain coats the outside, deep concentric grooves underneath prevent water from blowing upward. This completely dry inner ring forms an unbroken barrier. The current is trapped on the line, safely bypassing the wet pole. But while shaping the glass solved the problem of low-voltage leakage, it offered no protection against a multi-million-volt lightning transient ripping down the line. To stop massive surges, engineers placed spark gap arresters at the station window. These technical drawings show various metal plate configurations. Charles S. Bulkley's serrated comb arrestor, bottom left, harnessed point-to-plane field concentration, sharp brass teeth facing a grounded plate, separated by an air gap. When a lightning transient hits, extreme voltage concentrates at the tips of the sharp teeth until it exceeds the air's dielectric strength, ionizing the gas. This instantly collapses electrical resistance, forming an arc that routes the deadly surge directly to Earth, bypassing equipment. By intentionally sacrificing a tiny layer of air, engineers created a self-healing switch that closed only during emergencies and opened the millisecond the surge passed. Spark gaps handled instantaneous lightning, but couldn't stop sustained, slower overcurrents leaking onto the lines. To address that, French physicist Louis Breguet introduced a new device in 1847, the electrical fuse. The fuse operates on Joule's first law. Compared to a thick iron line wire, the smaller cross-section of the thin safety wire gives it an exponentially higher electrical resistance. When an overcurrent forces its way through that thin wire, it generates heat faster than the metal can dissipate it. The wire glows red hot, melts, and physically snaps apart, severing the circuit before the station instruments can burn. During the most extreme storms, however, the ultimate failsafe was the peg switchboard, seen here with its grid of brass holes and heavy patch cables. As a storm approached, operators manually inserted solid brass pegs into the board. This forcibly routed all incoming energy down sweeping copper wires, straight into large metal plates buried deep in moisture-retaining charcoal. Together, these insulators, spark gaps, fuses, and grounds created a physical defense system. It was a series of manual solutions that allowed the network to survive environmental surges by simply diverting the energy. In the 1890s, the electrical landscape shifted. The rise of high-power alternating current grids rendered those simple Victorian spark gaps dangerously obsolete. The problem with AC is a phenomenon called power follow-on current. Unlike a quick lightning strike, an AC grid continuously pumps electricity into the ionized arc, maintaining the short circuit instead of letting the spark extinguish. This sustained energy forced engineers to invent entirely new types of suppressors. Yet, the Victorian principle of the carbon spark gap remains the gold standard in high-end surge protection today. These early defenses were effective because the network was built from low-power, manual components. It was a system that could be physically severed and grounded by a human operator whenever the environment became too dangerous. Which brings us back to 1859. As this historic photograph of an early telegraph office reminds us, the Carrington event hit a network that could handle the blow. It sparked some paper, melted a few fuses, and ended up giving operators free power for a couple of hours. If a Carrington-level storm hit our grid today, it would induce massive DC-like currents that our modern AC infrastructure simply isn't designed to handle. As you can see in this simulation, those currents would saturate the solid iron cores of high-voltage transformers worldwide, causing them to warp and cook from the inside out. Our highly complex civilization lacks the physical failsafes of the Victorians. If the sky catches fire again, we can no longer save the network just by pulling a brass peg out of a board.